Hey everybody, this is Larry. This is day Q4 of the weekly contest 236 that I'm going over finding MK average. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem and in general. So for this problem, during the contest, I had some issues with reading. I actually tried to solve the one where it didn't have just the last M elements, so I was just a little bit weird out, but yeah. So I tracked the entire thing, but so I had to restart and reset my mind to the last M problems. I also had a weird typo somewhere, but the idea I had, and you can do this in other languages. You may use multi-set or something like that in C++, but in Java, in Python, I used sorted lists. And you can actually use any like sorted list structure, like binary, like a balanced binary search tree or something like that. Basically, just a way to basically just a data structure that allows you to get the min and the max in efficient time, and also remove elements in log n, add elements in log n, get the min and the max hopefully in O of 1, where O of log n is fine. And did I say log n for add? I mean log n for n, and also O of log n removal. Then that would be, that's my benchmark for knowing that'll be fast enough. So what I did is actually I wrapped the sorted list with a thing called sorted list with sum. I need to add more functions to make it like more useful, because I end up, but the idea here is that I have this class that gives me, what we said about the abstract data type of this tree like thing, that you add a thing to keep track of the total of the sum that is inside that thing. So basically what I did was that for implementation, I basically have 3 lists. Right, so I have list A. Let's say A, B. Oh, my computer's slow. Let's just say A sub 1 or A1, A2, A3, and then dot dot dot. Well, maybe not dot dot dot. The dot dot dot's inside. You have the middle, which is A4 dot dot. A sub, whatever, some other number. A sub j, and then some other boundary of and then A sub m, right? And maybe A sub m minus 1. Oh no, this is A of m because it's 1 index. And the idea is that, okay, you want this left side to always hold the invariant that is going to have k elements. You have the right side also k elements, and then on the middle, that becomes clear that it is just m minus k and minus k, or k, m minus 2 times k or something. And so those are the length of the list. And as long as we're able to move items from left, from the lists to each other, then that's all. All we have to do is make sure that we hold this invariant. And that's the key observation, or that's the key solution for this problem. As long as you're able to do that, it doesn't really matter, or other stuff doesn't really matter. As long as you're able to do that, hold that invariant. And having this sorted list data structure will allow us to do that. I do this in a very funky way, perhaps, but basically what I do is I literally if we have more lists, it may get a little bit confusing, a little bit trickier, but maybe you need to binary search the list itself to figure out which list to insert to. But because we only have 3 lists, I did it very manually. Basically, I tried to add, let's say we added a new number, x, right? So I try to put x inside the smallest k elements. And if it's inside, if x goes here, then we have the extra element that's, so A sub, we'll remove this biggest element, and then we'll try to put it here. And once we put that here, well, this number will, this will be already too small, so then or too many items, so then we put the next number here, and so forth. Basically, like a cascading addition, right? And then removal is the opposite. Basically, I try to remove from the large, or I try to see, is it in the largest section? If it's not, then you try to see if it's in the middle section. If it's not, if it is, then we remove that number, and then we take numbers from bigger, like basically cascading down and cascading up. And because every operation is log n, in theory, that should be fast enough unless your log n gets really expensive. And that's basically my idea. And then we have this buffer here that allow us to just keep track of the last m's, because in the beginning, you need to at some point remove elements. And then when you remove them, you do stuff. And then if you add them, you also do stuff. And we'll go over in a second. Let's go over to calculate m sum average. Given this, keeping in mind that every time we add a number to a sorted list or your tree-like structure, we keep track of the total. So then this is really easy then, because you just look at this total and then you divide it by the dividend, right? I think this is, this is what it sounds like. Hopefully, I don't need to explain this part, because if I do, you might need to work on easier problems. But yeah, this is a data structure problem. But yeah, basically, for each element, we add an element. If the buffer is too big, we have to remove something from the list. So here we take the first item, and this is the item that we're moving. This is just, this is usual sliding window stuff, if you will. As you slide the left pointer from left to right, this maybe reverse on your screen, but from left to right, you remove an item, and that item is the thing that you remove from the greater data structure. So first we try to remove from the right. If it's removed from the right, this is done. If we try to remove from the mid, then yeah, we remove from the mid, we take the smallest element from the right, and then we put it to the mid. So basically, depending on how you like to solve this problem, you have to maintain your invariant. And the way that I do it is that whenever I remove an element, I always push everything all the way to the left as much as possible, almost like three sorted lists next to each other. Well, and that's what it is. So yeah, so if it's less than m elements, the only element that's going to be missing is from the largest group. You don't have to implement it quite that way, but that's the way that I did it. Just, I don't know. But yeah, and if left has the or element, because or is not in left, is not in middle or the right, then the or is in left. And if it's on left, then we remove it from the left, and then we remove the smallest element from the mid and put it in left. And then we move the smallest element in the right, and then we put it in mid. Hopefully that makes sense. Like I said, I just cascade everything down. The smallest element, you pop, it's like musical chairs. Everyone push one over. And then addition is in the same way. So I add one to the left. If it overflows, and it should after, self.m, but this happens earlier. If this overflows self.k, which is the k that we're given, then we take the biggest element, and then we remove it and we put it in the middle. If there are enough elements in the middle, then you remove the biggest element from the middle, and then you put it into the right. That's pretty much it. I actually had a wrong answer because I wrote self.k here because I wasn't thinking. I was rushing it a little bit. And I didn't test. I should have tested. But yeah, that's all I have. And if you look at each of these things, and keeping in mind that sorted list, when I add and remove a number, I keep track of the total inside that region so that we can get this ready efficiently. So what's the cost, right? Well, this is going to calculate MK average is going to be O of 1, because this is just an O of 1, and this is O of 1 as well, and division is O of 1, say. So this is going to be O of 1. So what's the complexity of add element? This is where all the work is at, right? Well, you can go through this very slowly, and I'll go through it a little bit quicker, but let me know. But this is basically O of 1 because this is just a list, O of 1, and then the thing that's expensive is going to be the removals, and at most there's going to be 3 removals, and at the most there'll be 3 adds or something like that for the removal part, and also like the same amount. So like maybe at most 6 adds, 6 removals, something like that, which is constant number of adds and constant number of removals, and each add and removal is log n. So in total, or log m if you want to call it that. So in total, it's going to be log m. So add element is going to take log m time, and given that we're only given 10 to the fifth number of cores, that's going to be fast enough. Cool. That's all I have for this problem. Let me know what you think. I think once you get the concept, like I said, this is a data structure problem. So once you get the concept and you find the right data structure to match the performance profile that you want, then that's good enough. The biggest thing, of course, is just also keeping track of the total in an efficient way and having a data structure that allow you to do that. That's all I have. You can watch me solve it live during the contest next. I should have done that first, but I misread the problem twice. Sad. Okay. M and K, a stream of numbers. MK average. Numbers and less than M. Okay. Last M. The case. That's just two heaps, right? Maybe. Okay. That's ammo. Wrong done. Okay, so M is the number of elements that's inside, and K is the smallest. Okay, this is pretty straightforward. I wish I got Q3 not in a dumb way. Okay. How many queries are there? 10 to the fifth, so we have to be slightly better. And we don't remove any numbers, so once a number is removed, then it is gone. The only tricky thing is the beginning, I guess. Okay, let's just have a buffer. So we actually want this to be okay, and -1, right? Okay. Okay. What? The remaining, so this should be just self.total over self.n minus something like that. Yeah, should be okay. This should give me some random number. Must be a list. Did I do it the other way? Whoops, how did I? I literally just did it earlier today. This is way bad. -1, I get 0. Dun, dun, dun. Wait, I misunderstood something last. Oh, you only care about the last M. Not that it was more than M. Okay. Huh. I misread this one actually. Okay, then now what? It's still gonna be 2 heaps, but it's just a lot more annoying. And also because of the dupe numbers, it's a little bit confusing. Binary index tree. I missed the last M part. 45 minutes, should have enough time. Things you can do. Move the tree. How do you get this sum in a good time? I know you could do it with like binary index tree, but that's a mess. Is there an easier way? This is a little bit hacky, but let's try this. happened, man? I should forget how to do this. I have to overload something, but I forget how, so yeah, whatever. I'll have to do it later. Oh, I need a buffer as well. I need to remove first. Okay. This. That's still right. Okay. Let's see. This is not going to be right, but at least the 10 part should be right. Ugh. This abstraction was not necessary. Okay, 3 is right. The other one is not. That's odd. Oh, it's not odd because we just push everything too big because the invariant is not true. Oh, jeez. Oh, come on. Okay. Yep, that's what I thought it would be. Okay, yes, that's correct. Okay. Greater than. Is this linear? I actually don't remember. log in. Okay, that's good. Just want to make sure. Okay, so this is good, but now is it fast enough? Is this good? Yeah. Is this fast enough? Let's give it a YOLO, I think. Huh, wrong answer. Well, that's not expected, to be honest. Messy. My answer is 0, the right answer is 3. It is 3. Huh? 3, 6, 1, 6. Is my invariant wrong? My invariants are wrong, I guess. Why does this have 4 items? Keep adding. Oh, this is wrong. Okay, the middle one should have. Okay, silly Larry. Yeah, thanks everybody for watching this video. Hope this helped. And hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem and how did you do during the contest or just afterwards, observing or whatever. I'll see y'all next time. Yeah, stay good, stay healthy, take care of yourself, take care of others, to good health and to good mental health. I'll see you next problem. See ya.